chapter Rational Numbers.
This slide presents the overview of the chapter. Learning objectives. By the end of this chapter, you will be able to
identify the rational numbers. List the properties of the rational numbers. Represent the rational numbers on number line. Examine the rational numbers between two rational numbers. Write the decimal representation of rational numbers. Convert the decimal form into rational form.
Introduction. Before entering into the chapter, follow the instructions shown on the screen. Click each tab to know more.
We know identifying the number of same colored tiles out of total number of tiles in the above shown image. Here, the number of red colored tiles are 3 out of 16, which is represented as 3 by 16. The number of white colored tiles are 5 out of 16, which is represented as 5 by 16. Similarly, the yellow, black, green, and orange colored tiles are represented as shown on the screen. We know that all the number of colored tiles are in the form of P by Q, where P and Q are integers and Q not equal to 0, and are called rational numbers represented by Q. And these numbers are also known as quotient numbers. We also know that natural number can be represented as shown on the screen. And similarly, we can express any whole numbers and integers as shown on the screen. Thus, we conclude that all the natural numbers, whole numbers, and integers are also rational numbers. Do you know how to represent all the numbered colored tiles on a number line? And can you explain all the properties of rational numbers? Let us know all the properties of rational numbers under all operations, and also learn how to represent rational numbers on a number line and conversion of decimal form into rational form. Now, let us learn about properties of rational numbers. Properties of rational numbers. The properties of rational numbers are mainly classified into closure property, commutative property, and associative property. Again, each property is further explained for whole numbers, integers, and rational numbers. Now, let us learn in detail about closure property along with the operations under whole numbers, integers, and rational numbers. A set is closed under an operation if and only if the operation of any two elements of the set produces another element of the same set. If the operation produces even one element outside the set, the operation is not closed. Click each tab to know more. Let us see the closure property of operations on whole numbers. Under addition operation, it states that if two numbers are added, their sum is a whole number. For example, 2 plus 0 is again equal to 2. It concludes that the sum is always a whole number. Under subtraction, it states that the difference of two numbers is not a whole number. For example, 3 minus 6 is equal to minus 3, which is an integer. It concludes that the difference is not a whole number. Under multiplication, it states that the product of two whole numbers is again a whole number. For example, product of 7 and 0 is again 0, which is a whole number. It concludes that the multiplication of two whole numbers is always a whole number. Under division, it states that if two whole numbers are divided, the result is not a whole number. For example, 3 by 4 is equal to 0.75, which is a rational number. It concludes that the division of two whole numbers is not a whole number. Let us see the closure property of operations on integers. Under addition operation, it states that if two numbers are added, their sum is an integer. For example, 2 plus minus 1 is again equal to 1, or minus 1 plus minus 1 equal to minus 2. It concludes that the sum is always an integer. Under subtraction, it states that the difference of two integers is again an integer. For example, 4 minus 6 is equal to minus 2, which is an integer. It concludes that the difference of any two integers is also an integer. Under multiplication, it states that the product of two integers is always an integer. For example, product of 7 and minus 1 is minus 7, or the product of minus 2 and minus 5 is 10, which is an integer. It concludes that the multiplication of two integers is always an integer. Under division, it states that if two integers are divided, the result is not an integer. For example, 7 by 5 is equal to 1.4. It concludes that the division of two integers is not an integer. Let us see the closure property of operations on rational numbers. Under addition operation, it states that if two numbers are added, their sum is a rational number. For example, 1 by 2 plus 4 by 5 is equal to 13 by 10, or 2 by 6 plus 0 is equal to 2 by 6. It concludes that the sum of two rational numbers is again a rational number. Under subtraction, it states that the difference of two rational numbers is also a rational number. For example, 1 by 2 minus 3 by 4, which is equal to minus 1 by 4, or 4 by 7 minus 0 is again equal to 4 by 7. It concludes that the difference of any two rational numbers is also a rational number. Under multiplication, it states that the product of two rational numbers is always a rational number. For example, 1 by 2 into 3 by 4, which is equal to 3 by 8, or 2 by 7 into 0 is again equal to 0. It concludes that the multiplication of two rational numbers is also a rational number. Under division, it states that if two rational numbers are divided, the result is not a rational number. For example, 1 by 3 is equal to 0.3333, which is not a rational number, irrational number. It concludes that the division of two rational numbers is not a rational number.